Good morning, everyone. Today we are going to present our senior design project, which is the Formula SAE Aerodynamic package. Our group consists of Santiago, Almario, Francisco, Sanchez, and myself, Miguel Rodriguez. Our advisor is Dr. Tremante. For those of you who doesn't know what SAE stands for, it is the Society of Automotive Engineers. So our main objective is to design, analyze, and manufacture an external carbon fiber body for the FIU SAE team. We want to optimize and improve the aerodynamic cars package from previous years. And lastly, we want to follow the requirements from the 2015 SAE rules book in order to be able to compete in the 2016 competition, which is going to take place in Michigan in May of 2016. So our main motivation, we want to help the team to reach better rankings in the competition. Also, we want to place the FIU name at a higher level in the international stage. And lastly, this is our first time we're utilizing our technical knowledge we acquired through curriculum into a real-world project.
So our design was mainly goal-driven. Our main goals were to reduce weight and the cost of the design by reducing the surface area of the body itself, which would in turn reduce the amount of material needed to manufacture. We wanted to make it serviceable by providing access to the internal components for inspection and maintenance. We wanted to reduce aerodynamic drag by creating a smooth surface and reducing frontal high pressure points. And even though our car would not reach speeds where any significant downforce would be created by the body itself, we did use some downforce generating concepts to inspire our design. Mainly that would be like the high nose of the Formula Ones, which serve to scoop air under the car, accelerating it. And by Bernoulli's principle, the acceleration of the air creates a low pressure area under the car, bringing it down. It's also driven by the rules of the Formula SAE and by their design restrictions. And of course, we gathered inspiration from some current designs from both the aerospace and automotive industry. So as you can see here, we had three initial iterations of the design. The first two, as you can see, feature the high nose that we wanted to have the air accelerate under the car. The first one is different from the second one in that the first one is very close to the body, therefore reducing the amount of material needed and streamlining it a little bit. The idea for the second one was to shield the suspension components from the air, reducing drag. However, this design, we found that we would use too much material, we would go over cost limits, as well as infringe upon restrictions from SAE themselves, which don't allow the body to be that close to the wheels. The third design was a bit more for experimentation purposes. So as you can see here, we have a flat nose design, and as well, we have some of the components shielded from the suspension, though not all of them. One very important aspect of all of our design was that the holes for the suspension components were already included in the 3D design, facilitating the cuts later on, so that we wouldn't have to be guessing where the cuts will be once the body is done. Our final iteration is a take on our first design. We modified it a little bit in order to bring the nose and the body closer to the body, reducing our material, since our main goal was to reduce the weight and cost. We performed some design validation using our software. As you can see here with the zebra stripe visualization, we can make sure that we have smooth surfaces all the way through the car and make sure we're not creating any kinks where air might become stagnant. Another important test that we did was the draft analysis. The draft analysis is particularly important because it determines whether the molds would be able to be machined with a CNC router that we planned on using, which is a 3-axis machine. So if you have any negative curvature, the router would not be able to reach those properly. It would also, the draft angle also determines how easy the part is to remove from the molds. Again, if we have any negative curvature, that will mean that the mold is holding the part down, and the mold will have to be broken for the part to be released. We also performed some software flow simulation. As you can see here on your left, we have a plot of air velocity over the car. As you can see here, we're creating two high-speed air areas under the car at the positions where the two axles would be. These two high-speed air areas create two low-pressure zones visualized here by this relative pressure distribution. The next step was to create a small-scale prototype in order to be able to visualize our design properly and to be able to present it to the FIU SAE team for approval. We did this by 3D printing 1/10 scale model and signing and penning it to create a nice visual representation of what our final design would be. Finally, in order to allow for both easy assembly and serviceability, we divided the whole design into 5 parts that would be manufactured separately. So each one will have its own separate mold. As you can see here, the nose was designed to be taken off quickly in less than a minute in order to reach suspension, steering, and braking components on the car. The rest of the parts are designed to be semi-fixed. They're easy to be taken out, but they do require for the suspension components to be taken on and off. However, these cover areas that do not need to be serviced constantly, so they can stay on the car. And as we can see here, this is a cross-section of one of the molds. This is specifically for the top middle part. We can see how we designed the holes into the molds. That way we can lay our material around it and already have that shape marked properly.
During the competition, most of the teams used one of 3 materials for the carbon fiber for the body of the car. They either use aluminum, carbon fiber, or fiberglass. We chose to use carbon fiber as it is lightweight and due to its strength abilities. The manufacturing phase is composed of 3 main components. First, the CNC machining process of the actual individual molds. Then, the creation of one mold with the molds created from the first process, and then the vacuuming process where we lay the carbon fiber. One of the main differences of creating the body in our project was that, with respect to last year's body, was that they created a male mold, while this year we created a female mold, which you could see here. So it's a hole, and then last year they made an actual male mold. The advantages of this is that creating a female mold provides a better surface finish at the end of the process. For the CNC machining process, we had to take into consideration the CNC parameters that were provided with the machine that we used. We had a work area of 4 feet by 8 feet, and the CNC machine cut down in 11 inches of depth. Even though it was able to cut down 11 inches in depth, we were only able to cut down 3 inches in depth because of the drill bit that we had available to us in the shop. After we were able to cut the individual 3-inch pieces that you could see in this mold, we then brought the pieces of one of the molds, which you can see here, together, and we glued them together to create one mold. After that, we had to apply gel coat on the material to get a better surface to work with and apply the carbon fiber on the material. And the arduous sanding process started after that. Once we got the surface smooth with the sanding and then waxing, we started the vacuuming process, which consists of different layers, starting with a peel ply material, then a cotton material, which is a breather material, which allows during this process to take more resin out of the body, so it weighs less. And then we have a vacuum material to seal the entire system. This is one of the finished molds that we have, and here you can see 3 of the molds together on top of each other. Some of the standards that we used in the project were mainly came from the SAE competition rules and regulations, but we also had to adhere to the chemical properties that we were using with respect to the gel coat and the activating material on the gel coat. So at all times when we were working in the process of manufacturing and laying the molds, we were wearing safety glasses and face masks in order not to breathe in the chemicals, as well as in occasion we were wearing full body suits in the sanding process. Taking note from the American Society of Mechanical Engineers and the National Society of Professional Engineers Code of Ethics, we were adhering to provide a safe environment during the entire process for our members, the FIU team, and all the individuals that were helping with us in the process. We were serving the team in order to provide a better output of the design for this year, and in order to better the university team, the FIU name at the competition, and our abilities as engineers. For lifelong learning throughout the process, we were constantly learning new ways of how to do processes, and while we were learning each of the steps in the manufacturing process, as well as the design process, we were taking into consideration how things have been done in the past, how things are currently being done in other teams at the SAE competition, and how we could potentially make them better in the process, so the next years the FIU team can make the processes better.
Okay, so for the elements and evaluation of global design, we have to interact with the global community, reaching to local and international industry. It was basically they could participate as a sponsor, and also to provide education in the methods and processes that they were necessary for senior design projects to be successful. Also, what we did is that we reached different companies like Techstream in Switzerland, which they donate us the carbon fiber. Also, Aerotech in California, they donate us the bagging materials. And lastly, we had the opportunity to talk to the SAE FIU alumni, which right now they work for Chrysler, and they provide us with some of the knowledge that they had, and also some of the feedbacks of our process. This is our initial cost analysis. The total was $8,470. This was one of the biggest problems that we faced in our senior design, because it was money. So what we had to do is to look for a sponsorship. And with the help of the FIU SAE team, local, out-of-state, and international companies, we were able to reduce our final cost analysis by more than 90%, which it was a total of $506. And the biggest saving that we had, it was a CNC cut, which it was donated by a local company, and also the carbon fiber, which it was donated by a company in Switzerland. This is one of the most important tools that we utilize in our senior design, the timeline, so we couldn't fall behind. Also, on the left side, we have the division of responsibilities. They were divided in three main phases: designing, analysis, and manufacturing. Francisco Sanchez led the design phase, Santiago Almario led the analysis phase, and I led the manufacturing phase.
So some next steps that we're looking forward to taking is especially important is the compilation of all the documentation and all the knowledge we have gained throughout this process. There was definitely some process that we tried that had never been tried before. There were some processes that we made better from previous years. And all of this we want to put together and present to the FAU's SAE team to support a collaboration and collective learning, which will help the team keep on being more and more successful as the years go by. We also look forward to, once the car itself is finished, putting the new body on it and doing what we call a coasting test to compare it to the old model to get a final validation of our design. We also look forward to attending the FSAE 2016 competition, where we look forward to supporting the team both with the assembly of the body itself and with the technical report writing, as well as gain feedback from the industry on our design. So we want to give special thanks to obviously all of the people that were very helpful. We definitely could not have done this project without knowledge from the past teams or from the companies that donated all of the materials, which as you can see was the biggest constraint for our team. We will now take any questions if you guys desire. Thank you very much.
I'm really interested in the cost difference, because I know you got all this stuff donated and all that, but it's a small portion of the car. For example, what's the weight savings compared carbon fiber to fiberglass for the whole vehicle, for example? What's your savings in weight compared to the expenditure in cost, right? So I would be interested to see how much more expensive that costs for what savings you get in weight. Did you figure out exactly how much the whole thing's going to weigh?
We didn't calculate the exact numbers, but fiberglass is maybe, it also depends on the number of layers that you apply on the material. But the fiberglass material is, I would say, 1/3 heavier than the carbon fiber, each of the layers.
So you're saying it will be 33% heavier?
Around that number.
And what's that? You don't know the weight of that right now?
No. That also has to do with the actual the resin that's impregnated in order for the fiber to harden.
Right.
And we reduce the weight of that by through the vacuuming process with the cotton material to absorb.
Right, because what I'm looking at is, it's nitpicking, but if you're spending an extra $3,000 to save a pound, you know what I'm saying? Is that worth it? So it's just a matter of, you know, looking at it, but it's nicer with carbon fiber.
I have two questions with it. The first one is, if you weren't working off of a pre-built chassis, how would you have divided up your mold differently? So obviously this is the nose cone. This is one part of the whole chassis, the whole package that you put together. How would you have divided that up differently if some of the limitations that were there weren't there?
Well, what we look to do is to see which parts were important, not so much structurally, but as well as like considering the airflow in the car. So for example, we would never have done the nose divided right down the middle, because that would create somewhere for the air to come in at the highest pressure point and separate it. So what we looked to do was to have the less cuts possible, both for aesthetics and for structural integrity. So if we didn't have a chassis to work with, I would say we probably have done bigger pieces, and which means less pieces overall.
Did you ever look at any possibles? I think you mentioned that the remaining panels required suspensions to be removed and other components to be removed for access. Did you ever look at dividing it around, for example, your suspension plate, making that your dividing line?
We did, in fact, the front, the whole front pieces are designed that way. The top and bottom middle pieces are designed to go around the suspension. If you can see in this mold right here, they have cuts for the suspension. So this is the bottom part, and the top part would go the same. So that we designed for that. The rear parts, however, we wanted to again have the less pieces possible. And we talked to the team. We talked to them about what their needs were. And then we figured out that the rear part of the body would not need to be accessed that often, and that we could go ahead and have take the hit on not being able to take the rear of the body off without the suspensions, since that would probably not be done very often at all.
And then my second one was, I saw in your report you guys used the water tunnel testing to give yourselves an idea on a scaled model. Did you do any similitude for taking into account the difference between the scaling and the fluid difference when you moved from a scaled model in a water tunnel to what would be a full scale in air?
We did. The main parameter that needs to be correlated between those two, especially since we're using different fluids, is the Reynolds number of the flow. So we did take that into account. However, results for the water tunnel testing were pretty inconclusive. The reason for that is various things. The main reason was that we couldn't, with the resources that we had here at the university, we couldn't accurately measure the speed of the flow. The dye that we had available to see the streamlines was not visible at all on the video. So we did try to perform the testing, but the results were pretty inconclusive. So we decided not to. There's nothing that's worth presenting. So.
Well, going back to the fluid measurements, I don't know if this still works here, because I used to use a Doppler anemometry system here on campus. It was a laser. You could actually measure flow, very small flow on inside the system without even touching it. Just putting seeding in there like reflective particles, and then measuring the flow with that. So that would have been interesting to do that.
Did you do any wind tunnel testing?
We did not.
So why is it in your presentation on the board and in two places?
It's on the timeline because we did have plans of doing it, making time for it.
It's also in your presentation.
Was it? Okay.
Yep.
That might have been a mistake that slipped through us. At the end of the day, we did not have the necessary resources or our time available to do the wind tunnel testing.
Okay. When you finished, are you completely finished making the body at this point?
It's about it's 3/5 finished.
3/5 finished.
So the two remaining molds are ready for manufacturing, and then the process for the carbon fiber layup takes about 3 days.
Okay. Have you done any dimensional work on the parts that come out of this system to confirm that they meet your print?
Yes. So with the three.
So why didn't we see that?
Oh, there's a picture there of the.
Yeah,
Not a
there's one
picture.
picture there.
Okay.
No, I didn't want to see a picture. I want to know the dimensions here, match the dimensions that you did simulation on. I want to make sure that what you made is what you said you made.
Okay, right. We did not do any dimensional validation like that.
Well, I mean, the design that we did in SolidWorks is CNC the machine exactly to scale on the actual foam pieces. So these pieces are one-to-one to what we designed on the actual SolidWorks.
And you do believe that the one-to-one in the SolidWorks translated to one-to-one on the finished part?
Yeah. I mean, these molds are exactly, well, it's not exactly one-to-one because there's layers to consider here. But when we mounted the 3 pieces that we have, they did fit. And this is an exact replica of what we have in the design in SolidWorks, of the molds.
To add to that, the way we made sure that it was gonna be the same dimensions that we needed it to be is that we received the chassis files, the 3D chassis files from the team, and we designed the body in context with on the body within SolidWorks.
The chassis that are already built.
Okay, and my last question, the holes that you put into the bodies, have you at this point checked that they match where the holes ought to be?
We have not been able to do that since the car is not fully assembled yet, so we will finish that validation once the car is fully assembled and we're able to put the body on it.
But those components are also already included in the SolidWorks file, which is why we place those holes in that specific part, because they're already built into the SolidWorks chassis and system of the car.
Okay, thank you.
To tell you a little bit about the vacuum bagging, you showed that, but it looks like a pretty complex process.
It's a long process.
So I don't know much about it. I see, boat builders use it all the time.
Okay.
But I'm just curious how you guys did it, vacuum pump and
Yes.
plastic bags. And
So before the vacuuming process, the first thing is to have the mold complete. So after you have the mold complete and you have it completely sanded and soft and smooth, you gotta wax the actual mold.